Discovering differentiation. Drawing tangents to graphs is not always practical, so the process of calculating the gradient of a curve is called differentiation, and the result is called the derivative. To do this, we use what's known as a limiting chord process. Now the idea is shown in this diagram here. So here we have a curve or a function, and we've got 2 points as we can see. So if we say that the function is y is f of x, and we say this point is the point P, x, y, and this point is the point Q, x plus delta x, y plus delta y. So what we're saying is here, on the function y equals f of x, let the point P, x, y, and the point Q be x plus delta x, y plus delta y. So we're saying that this gap here is delta x, and then delta y is this gap just here. The horizontal distance between P and Q is delta x, as we just pointed out. The vertical distance between them is delta y. This means the gradient of the chord joining P and Q could be written as m is y2 minus y1 over x2 minus x1. Remember, that's the formula for a gradient. And in this case, that would be y plus delta y, take away y, so that's the difference in the y coordinates, over x plus delta x, take away x, the difference in the x coordinates. And that's equal to delta y over delta x. If we bring the point Q closer and closer to point P, the distances delta x and delta y become smaller and smaller, and the gradient begins to approximate the gradient of a tangent. So let's just think about that. If we've got the tangent line here, like so, then clearly the gradient that we have at the moment is not the same as that, but we're talking about bringing this point closer and closer to P until they're virtually indistinguishable. We won't actually be allowed to make delta x equal to 0, because then we just have 1 point and we can't calculate a gradient, but we can make it as close to that point as we like. And then we write the gradient of P, so the gradient of the tangent of P, as the limit as delta x tends to 0 of delta y over delta x. So delta x can't actually be 0, but we can make it as small as we like, so a millionth, a billionth, or even much, much smaller than that. In practice, we replace delta x with h and delta y with f of x plus h minus f of x. Should be reasonably clear where that's come from, but we could explain it still further. So we have our curve here, and we say this is the point P with coordinates x and y, and then we say, instead of saying that this distance here is delta x, we say it's h. So this is the point Q, and the x coordinate here is x plus h, and the coordinate there will be f evaluated at x plus h, just like the y down here would be the function evaluated at x. So we can see the difference in the y coordinates is f of x plus h, take away f of x, which we have just here. So the gradient of the tangent at point P can be written as the limit as h tends to 0 of the difference in the y's over the difference in the x's, which is just h. And remember, what we're doing there is shrinking Q towards P, and that's where the h tends to 0, because the h is the horizontal difference between the 2 points.